Hi, third graders. I am coming to you on Wednesday night, but you will be watching this on Thursday morning. We are going to talk about primetime lesson 4.3. I would like to start by talking about the questions from yesterday. I heard from a few people that they had they wanted some feedback on if they did the work right. So, why do we say the prime? Oh, also, I could say if you don't want to watch about 4.2, you can just zoom ahead a little bit. But anyway, on 4.2, if you answered question A, we say the prime factorization instead of because there is only one. In B, you were supposed to find the prime factorizations of those three numbers. So 72 is 2 by 2 by 2 by 3 by 3. 120 is 2 by 2 by 2 by 3 by 5. And 600 is 2 by 2 by 2 by 3 by 5 by 5. And then it asked you to write those using exponents. So remember, an exponent is the little raised number that says how many times a number is repeated or a factor is repeated. So 72 was 2 to the power of 3 times 3 to the power of 2. 120 was 2 to the power of 3 times 5. And 600 was 2 to the power of 3 times 5 to the power of 2. Question D was a little bit more difficult. So in question 3, it asked you to choose a composite factor of 72. Show how that composite factor can be found in the prime factorization. So I'm going to write it out, I think, with some text here. So the prime factorization of 72 was 2 by 2 by 2 by 3. Oops. By 3. Oh no, now it's going to be slow, huh? Let's see. By 3. No. By 3. Well, I guess we're just going to have to deal with that. Are we okay with that being a little off? Whoops. All right. Well, so what do we do with that? We find what is one of the composite factors of 72. So I'm going to choose 9. Okay, so if I choose 9, how do I find 9 in the prime factorization of 72? Well, I see 3 times 3 is 9. So here I would write 9 equals 3 times 3. All right, sorry for my bad handwriting. I have a mouse on order, but I'm just using my touchpad and it's kind of hard to write with. This composite factor, now for D2, this composite factor is a part of a factor pair for 72. How can you use the prime factorization to find the other factor in the pair? So 9 times 8 is what equals 72, right? So 8 was the other factor pair. And how do we find that in our original prime factorization? Well, 2 times 2 times 2 times 2 is 8. So you can find, if you find one factor, excuse me, you can use the prime factorization to find the other factor. Then it says find a multiple of 72. What will the prime factorizations of this multiple have in common with the prime factorization of 72? So I'll try this again. So my prime factorization was 2 by 2 by 2 by 3 by 3. So that was 72. What would be my next one would be 144, right? Because 72 plus 72. So what would that prime factorization have in common? It would have in common all of this plus what? Plus another 2, right? Because I doubled 72, so it would have another 2. So we'll talk more about that today in our lesson 4.3. So in 4.3, they're talking about using prime factorization. So you may remember back in the last investigation when we made the Venn diagrams, and Derek wanted to find the common factors and common multiples of 24 and 60. He made Venn diagrams similar to the ones we made in problem 2.3. So 2.3 was a little while ago, but I'm sure you remember those Venn diagrams. He conjectured and conjecture is a math guess, that he could use the prime factorizations to find common factors. So first he found the prime factorizations of 24 and 60, and those are listed here. Both of those prime factorizations have 2 by 2. So because they both have 2 by 2, that means that they have 4 as a common factor. And then it says both have 2 by 3, which would mean that 6 was a common factor, right? So then he noticed that the longest string that they both had was 2 by 2 by 3. So let's go back to that. So do you see here? They both have 2 by 2 by 3, and this one has 2 by 2 by 3. So then their greatest common factor would be the answer to 2 by 2 by 3, which is 12. Right? And then he checked with his Venn diagram, and he was correct. Dirac wondered if he could use a similar method to find the least common multiple. So he realized that the prime factorization of any multiple of 24 would have its prime factorization. And that's what I was just talking about in our last thing with 72, right? So anything that is a multiple of 24 will have 24 in it, because you're going to be counting by 24s. So it will have at least that inside of it, right? Same as the prime factorization of 60 would have all of its numbers in it. So then he thought to himself, he said, I think that the prime factorization of any common multiple would be 2 by 2 by 2 by 3 by 5. So how did he get 2 by 2 by 2 by 3 by 5? Well, I see that this one has 2 by 2 by 2 by 3, so it includes all of that. And this one is 2 by 2 by 3 by 5. Does my prime factorization include all of that? Yes. Ooh. So he has combined it so it includes the prime factorizations of both of those numbers. And so he was correct. So you are going to use the prime factorizations of 72 and 120. We already found those. If you have your paper from yesterday, you should find that again. What was the longest string common to both factorizations? So what is the prime factorization that would include all the numbers that both of them have? Remember on here, we did not repeat this 2 by 2 by 2 by 3 by 2 by 2 by 3 by 5. Since they both had 2 2s, they just left the 2 2s. Since they both had a 3, they left the 3. This one had one extra 2, so they put it in. This one had an extra 5, so they put it in. So that was the longest string common to both. What is the greatest common factor? How do you know? Then it says, what is the shortest string of factors that has them both? Can you find a smaller common multiple? Can you find the greatest common multiple? Can you find the greatest common multiple? Is that possible? The next one says numbers whose greatest common factor is 1, like 25 and 12, are called relatively prime. That's yellow because it's a new word. How can you determine that 25 and 12 are relatively prime? By looking at their prime factorizations. So again, this is looking at the prime factorizations of 25 and 12. So 25, I know, is 5 by 5, right? And 5 and 5 are prime, so that is their prime factorization. And then 12 is a little harder for me to do, but I'm just going to take a guess here. 12, I know it's 4 and 3 makes 12, so it must be, I feel like we just did this. 2 by 2 by 2 by 3. I think this was in your ACE answers. So why do you think those are relatively prime? Their greatest common factor is going to be 1, because they don't have anything in common. So again, up here, you were looking for the longest string common to both to find their greatest common factor. And here you're finding the shortest that has them both to find their greatest common multiple. So if this way of doing it is confusing to you, you can just find the greatest common factor and the least common multiple. We'll call it the old fashioned way, the long way, by counting by 72s and counting by 120s, or by finding all the factors of 72 and 120. The benefit of using this way is that you will find it, you will be accurate more often because you won't miss a factor or count wrong. Then in question D, you have some examples to answer, and that would be the end of this lesson. So you may not have time for homework tonight. It seems like that might be enough, that work. But if you do, you're welcome to do it. And if you don't, or you're worn out after a long day, that is okay with me. For my video tomorrow, I will go over today's work and we will be working on the investigation for review. So I hope you guys have a great day and I miss you all and I will see you soon.